1, so mu is, sorry, neutrino energy is theta. So it's E squared minus squared. Okay, so what you can do is essentially bring the u over here. So m pi c squared minus mu equals square root of u squared minus c squared. And very easy, just square both sides, solve for the mu. So to just carry that out. Squaring this gives m pi c squared minus 2 c squared plus e u squared equals u squared minus c squared, right? It's off, and we are simply left with a linear function. We solve that. It tells you that the energy of the new one is pi squared u squared c squared over. Alright, so we know the energy of the mu1. With this, we also know the momentum of the mu1. How would you calculate the energy of the neutrino now? It's not difficult. We have to go through the same thing again for the neutrino, or what do we do? The energy of the neutrino we can calculate how. So we don't need much space for that. Sorry. But we don't know the momentum either, right? But we know what the total energy is, right? The total energy is the pi inverse mass energy. So we can simply use that to calculate the neutrino energy, and y c squared minus e. So that was the second example, how you can use simple energy momentum conservation just to calculate the final products, the final energy and momentum. Good. Can we say anything about in what direction these momenta will go, like this or this? Not really, right? Because this is all symmetric, so this will be essentially a random thing where they go. But what do we know about the momenta again? They are going exactly in opposite directions. So whatever direction one particle goes, the other one must go exactly in the opposite direction, because we start off with zero momentum. Okay. Any questions about this? Do you think we should discuss more? If not, then one last and especially for astrophysics very important example. That is Compton's measuring, especially in relativistic astrophysics. You see actually that high energy radiation gamma rays are often made by this Compton's measuring process. So let's talk about it a little bit. The situation here being that we have some electron that's at rest, and we have a photon coming in, scatters off the electron. So let's call that energy of the incoming photon here. and that will be scattered off in some direction, E out. And as a consequence, the electron obviously will have to pick up some of that momentum here. Right? So the electron will probably go out in this direction, P out. Right? Okay, should we play that same game again? What's the total momentum coming in? And that is, well, the form momentum of the photon here. Form momentum of the photon, you can read from there. This E in over C. 1 and in whatever direction this goes, so let's call K the direction of propagation of the photon before, or actually let's call in here. And let's say after scattering, the photon goes in some other direction. K out. Do we have more form momentum than before state? Anything missing? Nothing missing? Everybody agrees that there's nothing missing? What's the form momentum of a particle at rest? It is not zero, right? The 3 momentum is 0, but the 4 momentum is not. So we still have the electron that is just at rest, right? So 0. That we shouldn't go forget. Okay, now on the outgoing side, so P going out equals, now we have the outgoing photon here, right? E out over C, 1 and K out. Plus, and now we have the energy of the electron that goes out over C, and the momentum of the electron as it goes out. Right? Okay. So, the easiest way actually to solve this, so this is, let's call this P in plus P electron going in equals P out plus P electron out. The trick that's often very helpful is to square this. So do the Lorentz 4-vector product with itself. That often simplifies calculations. In this case, it really does. So if we do that, we end up with form momentum of the photon squared plus 2 P in but electron in plus P electron in squared. And on the right hand side, we have form momentum of the outgoing photon squared plus 2 P out dot P electron out plus P electron out squared. Now this simplifies things a little bit. What is the form momentum of the incoming photon squared? So form momentum of the photon with itself, 4-vector product. Right here. P dot B, MC squared, but for photons, it's 0. Right? So this is 0. This is a photon as well. That's also 0. And what is it for electrons? For electrons, P squared, P dot P with itself, minus MC squared. So here we have MEC squared equals, you can write this here as well, plus, sorry, minus MC squared, good. So that goes here, that goes there. just need to figure out what is the P in dot E in. So that's the 4-vector product of this with this. So from this, we have, well, the 2 stays there. Since there's no velocity free component here, there's only the time component that comes in with a minus, right? So that is E in times ME minus. That's that part. And yeah, for the outgoing part, we have to do a little bit more. There's 2 times. So the time component, again, is minus 2 E out times the electron out over C squared. That's here. And then we have positive, the time, with the space components, plus 2 E out over C over C. We have K out dot P electron out. Right? Okay. So first, before we continue, we have this electron 4-vector product here on both sides, so that we can come out. And suddenly, this all begins to look quite nice, doesn't it? So, the problem is we don't know what the outgoing energy is here, and energy E out we don't quite know either, but we have energy conservation, right? Energy conservation tells us that ingoing energy of the photon plus the C squared, so that's the 0 component here, is energy of the outgoing photon plus E out, right? So there's one constraint here to get the E out. And the same with the momentum, so in over C, that's everywhere, E in times K in plus nothing is E out, K out, plus right? Just multiply the C over to everything. That is the space component of this momentum conservation. Okay, now we can write everything out in terms of ingoing energy, outgoing photon energy. So just eliminate, so E out equals E in plus MEC squared plus minus out. And this tells us that P E out equals, that here, E out equals E in over C minus out over C. All right, so let's see if that actually simplifies things a little bit. What we could probably do is just multiply C squared to everything here. This times C. Okay, then we have minus 2E in MEC squared equals minus 2E out. We know what that is. E out is E in plus MC squared minus E out. Okay, plus 2 E out times C times, and now K dot, so K in dot A out. So we have this here, E in over C K out dot K in. That's the first part here. Minus E out over C K out. Okay, let's see if we can simplify that a little bit. First, if we define, say, some angle theta by which we are scattering here, then what we have here, the 3-vector dot product of this vector and this vector gives us what in terms of the angle? That's the angle between the two vectors of which you take the dot product, the unit vectors, length 1. So the dot product gives you the cosine of the angle between, right? So that is cosine theta. What is K out, unit vector dot unit vector itself? Of course, it's just 1, right? So this totally forget. Alright, then let's see if there are terms that we can cancel out here. Minus 2e in NBC squared, minus 2e in, no, that stays, unfortunately. Maybe we can write all this out here. Prefer to stay on this board here. So, if we continue there, so we have minus 2 e in NBC squared equals minus 2e out e in minus 2e out NBC squared plus 2 squared, right, that's this part here, plus 2 e out e in, this one here, times cosine theta, minus 2 e out squared, right? Okay. Now it begins to look a little better. We have plus 2e out squared minus 2e out squared. Those go away. Now, what we want to get out is this out. Let's see if there's anything else we have here. Out that we wanted to. So let's do first of all, there's a 2 everything. So that we can out. So then we have E out, E in, minus cosine theta. squared, or we had the outgoing photon energy as, just divide by this, E in over 1 plus E over C squared 1 minus. Okay. I think this was actually a little bit more straightforward than the way that the book does it. So that tells you in particular, what photon energy comes out if we are not interested in the energy the electron picks up. So for astrophysics, this is quite an important process, because this means actually if you have electrons not at rest, but moving relativistically, you can actually boost photons up to high energies. That's one way that in astrophysics we can make X-rays and gamma rays high energy radiation. But let's first look at this expression here, so outgoing energy versus ingoing energy. If we're looking at very low energy photons, so incoming photon energy that is much less than the electron rest mass energy. So if this term here is essentially negligible compared to the 1, that means that the outgoing energy is equal to the ingoing energy. Which means if we are in this regime that the photons have very low energy, the scattered photon essentially doesn't change. The photon doesn't change energy. It's bounced off somewhere else, but essentially with the same energy. So this means it's elastic scattering, and this is something called the Thomson regime. So this low energy regime where the photons are just scattering off elastically, that's called the Thomson regime of photon scattering. Now if E in over mdc squared is much larger than 1, then the 1 essentially is negligible, and then we have the outgoing energy is approximately c squared over. So it's of the order of c squared. So if the photon comes in with an energy that's way larger than the rest mass energy of the electron, it means it comes out. So if it comes out with an energy that's much larger, so that means the in is much larger than NEC squared, it comes out with an energy that is about just 1 NEC squared. Means effectively, where's the energy then going? It has a lot of energy, much more than rest mass energy. It comes out with just about 1 rest mass energy. Where is that energy going? Must be somewhere. It's the energy that is essentially kicked out of our calculation. The energy that the electron loses, that the photon loses, must be picked up by the electron. So this means this is very inelastic. The photon scatters to very low energy, and all the energy goes into the electron. This is something called the Klein-Nischin element. Or Klein-Nischin energy. Good. So maybe one last thing on the Compton scattering. It's here. Photon energy. Of course, so photon energy, photon. How can we relate that to the photon frequency? Frequency of the light observed. There we go. Yeah. Planck constant times photon energy, that time times frequency. And of course the frequency is related to speed of light and wavelength as hc over lambda. Since frequency times wavelength is the propagation speed, which is the speed of light. Okay, so from that we can then simply relate this energy equation to a relation of wavelengths, meaning, so if you solve this out, is the incoming wavelength and then plus h over c squared 1 minus cosine theta. And right. And this term obviously has the same units of wavelength here. So this is often called the Compton wavelength. The natural constant obviously depends only essentially on the mass and charge of the electron. So this is something like 2.4 times 10 to the minus 10 centimeter. That's something called the Compton wavelength. This is the characteristic wavelength that describes the change of wavelengths of photons pair of an electron in Compton's pair. We had a little bit of modern physics, I think, right, with quantum mechanics. How does this kind of figure in with quantum mechanics? Quantum mechanics, how do you describe an electron? As the center of the particle, but that's not the quantum mechanical description. Right? Quantum mechanics, you essentially describe everything as waves or wavelengths. Right? So this is a characteristic wavelength of an electron, essentially, as it propagates. Good. And that's it for coffee. Any questions? If not, let's get some coffee and be back here.